A journey through the most mind-bending science ever discovered. What if I told you that the chair you're sitting on doesn't really exist until you look at it? That particles can be in two places at once? That your morning coffee is powered by the same quantum magic that makes stars shine? Welcome to quantum physics, where the impossible becomes routine and reality itself is far stranger than any science fiction. Welcome to this gentle exploration of quantum physics, where we'll unravel the mysteries of the universe's smallest scales. Whether you're here to learn, relax, or simply marvel at how bizarre our cosmos truly is, you're in for a fascinating journey. Let's dive into a world where common sense takes a holiday and nature reveals its most extraordinary secrets. The world beyond our senses, quantum physics, deals with the universe's tiniest building blocks. Particles so small they make atoms look like beach balls. We're talking about electrons, photons, and quarks, the fundamental pieces that make up everything you see, touch, and are. Here's the twist. These particles don't behave anything like the solid, predictable objects we encounter in daily life. They play by radically different rules, rules so strange that even Einstein struggled to accept them. In our everyday world, things make sense. Drop a book, it falls. Throw a ball, it arcs predictably. But shrink down to the quantum scale, and that predictability evaporates. The ball might not land where you expect. It might not land at all. It could exist in a cloud of possible locations until someone observes it. Then, and only then, does it decide where to be. This isn't science fiction. It's science fact, confirmed by decades of experiments. The two-world problem, classical physics, the kind you learned in school, describes the world of solid objects, gravity, and predictable motion. Everything neat and orderly. But quantum physics reveals that underneath this apparent solidity lies something far more mysterious, a realm of probability, uncertainty, and seemingly impossible phenomena. The fascinating part, both descriptions are correct. Classical physics emerges from quantum physics when enough particles gather together. It's like discovering that your solid furniture is made of invisible spinning coins, yet somehow your chair still holds you up. Why this matters, quantum physics isn't just abstract theory. It powers the device you're using right now. It explains how the sun shines, how atoms bond to create molecules, and how chemistry itself works. Without quantum mechanics, there would be no smartphones, no computers, no lasers, no modern medicine. Every chemical reaction in your body, every flicker of thought in your brain, every beam of light that touches your skin operates according to quantum rules. You are quite literally made of quantum stuff. So buckle up, we're about to explore a universe that's simultaneously weirder and more wonderful than you ever imagined. Experiment realities. First plot twist. The setup, imagine shooting tiny particles, electrons for instance, toward a wall with two narrow slits. Behind the wall sits a screen that detects where the particles land. Simple enough, right? If we close one slit, particles pass through the open one and create a single line on the screen. Close that slit and open the other, we get a different line. Basic physics. This is exactly what we'd expect from tiny billiard balls being shot at a barrier. They go through whichever hole is open and pile up on the other side in a predictable cluster. Now, open both slits. Logic says we should see two lines, a combination of the patterns from each individual slit. After all, each electron should go through one slit or the other, right? We should just see an overlap of the two individual patterns. But that's not what happens. The shocking result, instead of two lines, we see multiple bands, an interference pattern. This is what you'd expect from waves, not particles. Light and dark bands appear on the screen, showing constructive interference, where waves add up, and destructive interference, where waves cancel out. It's as if each electron is somehow passing through both slits simultaneously, interfering with itself like ripples in a pond. Think about that for a moment. An electron, a discrete chunk of matter with mass and charge, is somehow behaving like a spread-out wave. It's taking both paths at once and creating an interference pattern that only makes sense if the electron is aware of both slits. But wait, it gets stranger. One particle at a time, scientists slowed the experiment down, firing electrons one at a time. Each electron hits the screen as a single dot. No waves, just particles. But as more electrons arrive, the dots gradually form that same interference pattern. Each electron, traveling alone with no other electrons to interact with, still creates a wave pattern. It's as if each particle goes through both slits at once, even when there's only one particle in the experiment. The observer effect strikes. Here's where reality truly goes off the rails. When scientists set up detectors to see which slit each electron actually passes through, the interference pattern vanishes. The electrons suddenly behave like ordinary particles, creating just two lines. The act of observation fundamentally changes the outcome. It's not that we're disturbing the particles with clumsy instruments. It's that the universe itself behaves differently, depending on whether we're watching. What this means, the double slit experiment reveals three mind-bending truths. Wave-particle duality. Electrons and photons are neither purely particles nor purely waves. They're both, depending on how we observe them. Superposition. Until observed, particles exist in multiple states simultaneously, exploring all possible paths at once. Measurement matters. The act of observation collapses possibilities into definite outcomes. Before we look, particles inhabit a ghostly realm of maybe. This isn't philosophy. It's been tested thousands of times with ever more sophisticated equipment. The conclusion is inescapable. At the quantum level, reality is fundamentally probabilistic, not deterministic. Keeping your options open, superposition is quantum physics' most elegant concept. The idea that particles can exist in multiple states simultaneously until observed. Imagine flipping a coin. In our world, it's heads or tails once it lands. But in the quantum world, the coin is both heads and tails. Not just unknown, but genuinely both, until you catch it and force it to choose. This isn't uncertainty about what state something is in. It's the particle literally being in multiple states at once, a real, physical superposition of possibilities. Think of it like this. Before measurement, a quantum particle isn't choosing between options, it's experiencing all options simultaneously. It's not that we don't know which state it's in. It's that asking which state is the wrong question. The particle is genuinely in a combination of states, a weighted mixture of possibilities described mathematically by complex numbers. The wave function, that mathematical expression we mentioned earlier, captures this beautifully. It assigns probability amplitudes to each possible state, and these amplitudes can interfere with each other constructively or destructively, just like waves. When we finally measure the system, the wave function collapses to a single outcome, with probabilities determined by those amplitudes. This is verified by countless experiments. Atoms can be in superposition of different energy levels. Photons can be in superposition of different polarizations. Particles can literally be in multiple places at once, not metaphorically but physically, measurably, repeatably. Schrödinger's cat. The famous thought experiment, Austrian physicist Erwin Schrödinger illustrated this weirdness with a famous and darkly amusing thought experiment. Place a cat in a sealed box with a radioactive atom that has a 50% chance of decaying within 1 hour. If it decays, it triggers a mechanism releasing poison gas, killing the cat. If it doesn't decay, the cat lives. The atom exists in superposition, both decayed and not decayed until observed. Therefore, according to quantum mechanics, the cat must also be in superposition, simultaneously alive and dead. Schrödinger proposed this, not because he believed cats could be both alive and dead, but to show how absurd quantum principles seem when applied to everyday objects. He was essentially saying, look, if we take the Copenhagen interpretation seriously and apply it to macroscopic objects, we get ridiculous results like zombie cats in limbo. Clearly, something is incomplete or misunderstood. Yet that absurdity reflects actual quantum behavior at microscopic scales. The thought experiment highlights what's called the measurement problem, RA, the question of when, how, and why superposition ends and definite outcomes emerge. Is there a fundamental dividing line between the quantum and classical worlds? Does size matter? Does consciousness play a role? These questions have spawned competing interpretations of quantum mechanics, each trying to resolve the paradox Schrödinger so cleverly highlighted. The cat has become a cultural icon, appearing in countless physics discussions, popular science books, and even internet memes. But its real purpose remains to make us confront the strangeness of quantum superposition and ask what it truly means. Why we don't see quantum cats. Large objects don't maintain superposition because of decoherence. When quantum systems interact with their environment, air molecules, photons, heat, the delicate superposition collapses almost instantly. That's why your toast never exists in a superposition of toasted and untoasted states. But at atomic scales, superposition is real, verified, and incredibly important. The power of maybe. Quantum computing superposition isn't just weird, it's useful. Classical computers use bits that are either 0 or 1. Quantum computers use qubits that can be both 0 and 1 simultaneously. With multiple qubits in superposition, quantum computers can explore vast numbers of possibilities at once. 20 qubits can represent over 1,000,000 states simultaneously. 50 qubits? Over a quadrillion states. This makes quantum computers extraordinarily powerful for specific problems. Optimizing complex systems, simulating molecular behavior, breaking certain types of encryption, and solving challenges that would take classical computers millions of years. The philosophical implication superposition challenges our basic assumptions about existence. It suggests that before observation, reality isn't fixed but fluid, a sea of possibilities waiting to crystallize into definite outcomes. You might say the universe itself exists in superposition, filled with countless potential states, and observation is the process that selects which possibilities become real. Principle. Knowledge has limits. The fundamental boundary Werner Heisenberg discovered something profound in 1927 that fundamentally changed our understanding of reality. There are inherent limits to what we can know about quantum systems. This isn't about imperfect instruments or insufficient technology. It's about the nature of reality itself. The Heisenberg uncertainty principle states that the more precisely we know a particle's position, the less precisely we can know its momentum, mass times velocity, and vice versa. These two properties are fundamentally linked through the mathematics of wave functions. Knowing one erases knowledge of the other. The relationship is expressed mathematically as delta x delta p flash 2, where delta x is the uncertainty in position, delta p is the uncertainty in momentum, and h bar is the reduced Planck constant, an incredibly tiny number but non-zero. This inequality says there's a minimum product of uncertainties. You can never reduce both to zero simultaneously. But this isn't just about position and momentum. Similar uncertainty relations exist for other pairs of complementary properties, energy and time. The more precisely you know a system's energy, the less precisely you can know when it's in that energy state. This has profound implications. It allows virtual particles to borrow energy from the vacuum for brief moments, as long as they pay it back quickly enough that delta E times delta to 2. Angular momentum components. If you precisely measure a particle's spin in one direction, measurements in perpendicular directions become completely uncertain. You can't simultaneously know all three components of angular momentum precisely. These aren't separate phenomena. They're manifestations of a deep principle about complementary observables in quantum mechanics. Certain pairs of properties are linked such that precise knowledge of one necessitates uncertainty in the other. Why this happens? The reason lies in wave functions and Fourier analysis. In mathematics, there's a fundamental trade-off between localization in position and localization in momentum, or equivalently, localization in wavelength. A wave that's perfectly defined in position, sharply localized, must contain a wide spread of wavelengths and therefore momenta. A wave with a single precise wavelength and thus precise momentum must extend infinitely in space. It's not just that we don't know, but the particle genuinely doesn't have definite values for both properties simultaneously. Before measurement, asking, what is the particle's exact position and momentum, is asking a question nature itself can't answer because the answer doesn't exist. The particle is described by a wave function that encodes probabilities, not definite values. Think of it like this. Imagine trying to measure the exact frequency of a musical note that plays for only a millisecond. The brief duration makes the frequency fundamentally uncertain. You'd need the note to last longer to determine its frequency more precisely. Similarly, confining a particle to a brief moment, uncertain time, makes its energy uncertain, and confining it to a small space, uncertain position, makes its momentum uncertain. Why this happens? The reason lies in wave functions. Particles aren't point-like objects. They're quantum systems described by waves. A wave that's perfectly defined in position, sharply localized, must be spread out in momentum. A wave with precise momentum, a pure frequency, is spread out in position. It's like trying to photograph a firefly in the dark. Shine a light to see where it is, and you startle it, changing its motion. Track its motion over time, and you lose track of its exact location. Real consequences. The uncertainty principle isn't just theoretical. It has profound effects. Atomic stability. Electrons don't collapse into the nucleus because confining them to such a small space would give them wildly uncertain and huge momentum, pushing them back out. Atoms exist because of uncertainty. Virtual particles. The uncertainty principle allows particles to borrow energy briefly and pop into existence as long as they disappear quickly enough. The vacuum itself seethes with these temporary fluctuations. Quantum tunneling. Uncertainty about a particle's position and energy allows it to occasionally borrow enough energy to pass through barriers it classically couldn't surmount. A different kind of knowing, the uncertainty principle forces us to abandon the idea of perfect knowledge. At quantum scales, nature simply doesn't allow us to pin down all properties simultaneously. Reality keeps some things permanently blurred. But this blur isn't a bug, it's a feature. The flexibility and breathing room provided by uncertainty is what allows the quantum world to function. Without it, atoms wouldn't exist, chemistry wouldn't work, and we wouldn't be here to wonder about it. The deepest connection, quantum entanglement, might be the most mysterious phenomenon in all of physics. When two particles become entangled, they share a profound connection. Measuring one instantly determines the state of the other, regardless of the distance separating them. Separate entangled particles by light years, and measuring one still immediately affects the other. Einstein called it spooky action at a distance, and he wasn't comfortable with it. But experiment after experiment has confirmed it's real. How it works: create two entangled electrons with opposite spins. According to quantum mechanics, neither electron has a definite spin until measured. Both exist in superposition, but they're not independent. They share a single quantum state. Measure one electron and find its spin up. Instantly, the other must be spin down, no matter how far away it is. The measurement doesn't send a signal. It collapses the shared wave function, revealing correlated results. Here's what makes this so profound. It's not that the electrons were predetermined to be opposite. Until the moment of measurement, neither electron had a definite spin. They existed in a shared quantum state, a single, unified entity, despite spatial separation. The measurement of one instantaneously determines the state of both. Imagine twins separated at birth who, despite never communicating, always choose opposite colors when selecting clothes each morning. That would be strange enough. But quantum entanglement is stranger. The twins don't just make opposite choices. They have no choice at all until one of them decides, and at that instant, the other's choice is also determined, even if they're on opposite sides of the galaxy. This isn't just theoretical speculation. Entanglement has been demonstrated over distances exceeding 1,200 kilometers using satellites. Chinese scientists successfully established entanglement between a satellite and ground stations, proving that this quantum connection survives even through the harsh environment of space. Testing the impossible in the 1960s, physicist John Bell developed a way to test whether particles could have hidden variables, WAD predetermined properties that only appear random. His mathematical proof showed that if hidden variables existed, particle correlations would be limited in specific ways. When experiments were performed, the results exceeded Bell's limits, exactly as quantum mechanics predicted. The correlations were too strong to be explained by hidden properties. Entanglement is genuinely non-local. The universe is more connected than classical physics allows. Real applications entanglement isn't just fascinating, it's becoming technologically useful. Quantum cryptography. Entangled particles create theoretically unbreakable codes through quantum key distribution, QKD. Two parties share entangled photons. Any eavesdropping attempt necessarily disturbs the quantum state. Entanglement is delicate, immediately alerting the communicators that security has been compromised. Several companies already offer commercial QKD systems, and some governments use quantum encrypted communication for sensitive information. China has launched satellites specifically to distribute entangled photons for secure communication across continental distances. Quantum teleportation. This isn't Star Trek-style matter transmission where you disappear and reappear elsewhere. Instead, it's the transfer of quantum states between particles using entanglement as a resource. Here's how it works. Say you have two entangled particles, B and C, with B on Earth and C on a space station. You want to teleport the quantum state of particle A on Earth to the space station. You perform a special joint measurement on A and B, which destroys A's original state. This measurement produces classical information, just regular bits, that you send to the space station at light speed or slower. Using this information, someone at the station can manipulate particle C to recreate A's original quantum state. The state has been teleported from Earth to orbit, though no matter actually traveled, and no faster-than-light communication occurred. Scientists have successfully teleported quantum states over hundreds of kilometers using fiber optics and through open air to satellites. Quantum computing. Entangled qubits form complex networks that give quantum computers their power. In classical parallel computing, you run multiple processors side by side, each handling part of a problem. In quantum computing, entanglement allows qubits to explore vast solution spaces collectively in ways classical bits never could. The qubits aren't just operating in parallel. They're correlated through entanglement in ways that allow interference between different computational paths, amplifying correct answers while canceling wrong ones. This is what enables quantum algorithms like Shor's algorithm for factoring or Grover's algorithm for searching to achieve speedups impossible classically. Quantum sensors. Entanglement enables sensors with unprecedented precision. Quantum entangled photons can measure gravitational waves, detect magnetic fields at incredibly fine scales useful for medical imaging or mineral exploration, or create clocks so precise that they could detect relativistic time dilation from moving just a centimeter vertically in Earth's gravity. These technologies are moving from laboratories toward practical applications. What it means entanglement suggests that at the deepest level, the universe isn't made of separate, independent pieces. It's an interconnected whole where relationships matter more than isolated objects. This isn't just poetic language. It's what the mathematics and experiments consistently show. Particles that interacted once remain connected forever, no matter how far apart they drift. In a very real sense, everything that has ever interacted remains subtly entwined in a cosmic web of quantum correlations. The atoms in your body were once part of stars entangled with stellar material. Though those specific entanglements have long since decohered, the principle remains. We live in a profoundly connected universe where the notion of complete separation is ultimately an illusion of the classical world. Fields all the way down want to know what particles really are. They're ripples. In quantum field theory, the fundamental constituents of reality aren't particles but fields, invisible energy fields that permeate all of space. What we call particles are simply localized excitations, tiny waves in these underlying fields. Imagine a calm lake. That's a quantum field in its ground state. Toss in a pebble and ripples form. Those ripples are particles. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. Every type of particle corresponds to its own field. No such thing as empty space. This perspective transforms our understanding of the vacuum. Empty space isn't empty. It's filled with fields in their lowest energy states, constantly vibrating with tiny fluctuations. These vacuum fluctuations create virtual particles, brief blips of particles and antiparticles that pop into existence and annihilate almost instantly. They're too short-lived to be directly observed, but their effects are real and measurable. For example, the Casimir effect, a small attractive force between closely spaced metal plates in a vacuum, results from virtual particles. The vacuum isn't empty. It's gently seething with quantum activity. How forces work in quantum field theory. Forces arise from particles exchanging virtual particles. The electromagnetic force is mediated by virtual photons, the strong nuclear force by virtual gluons, the weak force by virtual W and Z bosons, gravity, hypothetically, by virtual gravitons. When two electrons repel, they're exchanging virtual photons that carry momentum between them. Forces are conversations conducted in the language of quantum fields. The vacuum catastrophe. Here's a puzzle. If vacuum fluctuations contribute energy to empty space, how much energy is there? When physicists calculate this, they get a number so enormous that the universe should have exploded moments after the Big Bang. But clearly, that didn't happen. The actual vacuum energy, related to the cosmological constant, is incredibly tiny, about 120 orders of magnitude smaller than the theoretical prediction. This discrepancy is the largest in all of science, called the vacuum catastrophe. Nobody knows why the vacuum energy is so small. It remains one of physics' deepest mysteries. A unified picture quantum field theory unifies matter and energy, particles and forces into a single elegant framework. Everything, light, matter, forces, arises from quantum fields in various states of excitation. You aren't separate from the universe. You're a particular arrangement of quantum field vibrations, a temporary pattern in the cosmic symphony. And that pattern, incredibly, is capable of contemplating its own existence. Breaking classical rules in classical physics, if you don't have enough energy to climb a hill, you can't get to the other side. Period. But quantum particles don't always obey this rule. Quantum tunneling allows particles to pass through energy barriers they shouldn't be able to cross. It's as if you rolled a ball toward a hill with insufficient speed to reach the top, yet occasionally the ball just appears on the other side. How it happens? Remember, particles aren't point-like objects but wave functions, spreads of probability. When a particle approaches a barrier, its wave function doesn't stop abruptly at the edge like a tennis ball hitting a wall. Instead, it extends into and even through the barrier. The wave function decays exponentially inside the barrier. It gets weaker the deeper it penetrates. But as long as the barrier isn't infinitely thick, some amplitude reaches the other side. On the far side, the wave function is weaker but still present, with a non-zero value. Since there's a small but real probability of finding the particle beyond the barrier, having tunneled through without ever possessing enough energy to classically surmount it, the particle doesn't gain and then lose energy. Rather, the quantum nature of its existence allows it to be found in places classical physics forbids. The probability depends on several factors: the barrier's height, how much energy would classically be required, its width, how thick the forbidden region is, and the particle's energy, how close it is to being able to cross classically. A very high, thick barrier makes tunneling extremely unlikely. A thin, low barrier makes it much more probable. Mathematically, the tunneling probability decreases exponentially with barrier width and height. This is why we don't see macroscopic tunneling. For large objects, the probability is so astronomically small that it might happen once in a time span vastly exceeding the age of the universe. But for individual particles at atomic scales, tunneling happens constantly. The sun shines because of tunneling. Here's why this matters. The sun wouldn't shine without quantum tunneling. Deep in the sun's core, hydrogen nuclei must fuse to form helium, releasing energy. But these nuclei are positively charged and repel each other. Even under the sun's intense pressure and temperature, they don't have quite enough energy to overcome this repulsion classically. They tunnel through the energy barrier instead. Without quantum tunneling, nuclear fusion wouldn't occur, stars wouldn't shine, and life wouldn't exist. Technology built on tunneling isn't just cosmic, it's practical. Semiconductors powering all modern electronics rely on quantum tunneling. Tunnel diodes are designed specifically to exploit tunneling effects. Scanning tunneling microscopes image individual atoms by measuring electron tunneling currents between a sharp tip and a surface radioactive decay. Radioactive decay also relies on tunneling. Alpha particles, trapped inside atomic nuclei, don't have enough energy to escape classically. But occasionally, they tunnel through the nuclear potential barrier and escape, causing the nucleus to decay. This isn't just theory, it's how we date fossils, power spacecraft, and understand nuclear physics. The philosophy of maybe tunneling embodies quantum physics' fundamental message. Impossibility is flexible. Things that absolutely shouldn't happen according to classical physics can happen, just with low probability. There's always a chance, a whisper-thin thread of possibility, and at quantum scales, that's enough to reshape reality. The unexpected connection. For decades, biology and quantum physics seemed worlds apart. Biology is warm, wet, and messy. Quantum effects are delicate, requiring cold, isolated conditions. How could life, chaotic, noisy, complex life, harness quantum phenomena? Yet evidence suggests nature discovered quantum mechanics long before we did. Photosynthesis, nature's quantum engine. When sunlight hits a leaf, its energy must travel from antenna pigments to reaction centers where chemistry happens. This transfer is remarkably efficient, far more than random molecular bumping would allow. Research suggests photosynthetic systems use quantum coherence. The energy excitation exists in superposition, exploring multiple pathways simultaneously, then collapsing into the most efficient route. It's like the energy knows the shortest path because it tries them all at once. Here's what makes this extraordinary. Quantum coherence is fragile. It typically requires isolation from environmental noise. Think ultra-cold temperatures and carefully controlled conditions. Yet, somehow, photosynthetic complexes maintain quantum coherence at room temperature in the chaotic, wet environment of living cells. Studies using ultra-fast laser spectroscopy have detected quantum beating, oscillations that indicate coherent superposition, lasting for hundreds of femtoseconds, quadrillionths of a second, in photosynthetic proteins. While brief by human standards, this is remarkably long for quantum coherence in warm, noisy biological conditions. This happens in warm, wet biological conditions where quantum effects shouldn't survive long. Yet they do, helping every green plant on Earth harvest sunlight with stunning efficiency approaching 95% in some cases. If we could replicate this quantum efficiency in artificial solar cells, it would revolutionize renewable energy. Birds and quantum compass, migratory birds like European robins, navigate thousands of kilometers with incredible precision. How? One theory, a quantum compass. Molecules in birds' eyes, called cryptochromes, may become quantum entangled when light hits them. Earth's magnetic field subtly influences these entangled electron pairs, changing the chemical reaction outcome based on the bird's orientation. Here's the proposed mechanism. When blue light strikes cryptochrome molecules in the bird's retina, it excites an electron, creating a radical pair, two molecules each with an unpaired electron. These electrons become entangled, with their spins correlated. Earth's magnetic field, though weak, affects how these entangled spins evolve over time. Depending on the bird's orientation relative to the magnetic field, the radical pair will preferentially form either a singlet state, spins opposite, or triplet state, spins aligned. These different states lead to different chemical products, which the bird's visual system can detect. The bird might literally see a pattern, a dark or light spot, or perhaps colored overlay that shifts with the magnetic field direction, providing a built-in compass overlaid on its normal vision. It would be like having an augmented reality display showing which direction is north, generated entirely by quantum processes in the retina. Disrupting these quantum states experimentally, using specific wavelengths of light or artificial magnetic fields, interferes with bird navigation, suggesting they genuinely use quantum entanglement to find their way home. Studies show that European robins become disoriented when exposed to radio frequency electromagnetic fields that would disrupt radical pair reactions, providing strong evidence for this quantum compass hypothesis. If true, this means birds have been using quantum technology for navigation for millions of years, long before humans discovered quantum mechanics. The quantum nose. How do we smell? The traditional theory says odor molecules fit receptor shapes like keys in locks. But some molecules with similar shapes smell different, while differently shaped molecules smell the same. The vibrational theory of olfaction suggests smell involves quantum tunneling. When molecules bind to receptors, their vibrations may enable electron tunneling at specific frequencies, triggering different smell sensations. While controversial, it hints that even something as ordinary as sniffing a flower might involve subtle quantum processes. Consciousness and microtubules? Some researchers, including physicist Roger Penrose, speculate that quantum effects in brain structures called microtubules might relate to consciousness itself. This is highly speculative and not widely accepted, but it represents growing curiosity about whether quantum mechanics helps explain phenomena classical biology struggles with. Evolution's quantum toolkit. If quantum biology is real, it suggests evolution discovered and refined quantum advantages over billions of years. Life may exploit superposition, coherence, and tunneling naturally, long before human scientists understood these principles. Every breath, every thought, every heart might be supported by processes reaching down to the quantum scale, a hidden layer of reality powering the miracle of life itself. Beyond binary, classical computers use bits, 0 or 1. That's the foundation of all digital computation. Every photo, video, message, and calculation ultimately reduces to strings of zeros and ones processed by transistors that are either on or off. Quantum computers use qubits, which can be 0, 1, or both simultaneously through superposition. This doesn't just make quantum computers faster, it makes them fundamentally different, capable of solving problems classical computers can't practically touch. Here's the key insight. A classical bit can represent one value at a time. A qubit in superposition represents multiple values simultaneously. When you chain multiple qubits together and entangle them, the computational power doesn't just add up. It multiplies exponentially. The mathematics behind this is elegant. A qubit state is described by a vector in a complex two-dimensional space, with probability amplitudes for 0 and 1. When you measure the qubit, these amplitudes determine the probability of each outcome. But before measurement, the qubit genuinely exists in both states, weighted by those amplitudes. This allows quantum algorithms to explore multiple solution paths simultaneously, not by trying each one sequentially like classical computers, but by leveraging superposition to evaluate them all at once. It's parallelism of a fundamentally different kind, not multiple processors working side by side, but a single system existing in multiple computational states simultaneously. Exponential possibility space. 2 classical bits represent 4 possible values, zeros, 0, 1, 10, 11, but can only be in one state at a time. 2 qubits can represent all 4 states simultaneously. Add more qubits and the possibilities explode exponentially. 10 qubits, 1,024 states, 20 qubits. 1,048,576 states, 50 qubits. 1,125,899,942,624 states. A quantum computer doesn't check possibilities one by one. It explores vast possibility spaces in parallel, then collapses to the answer. What quantum computers excel at, quantum computers aren't better at everything. They're specialized for certain problems. Shor's algorithm factors large numbers exponentially faster than classical algorithms, potentially breaking current encryption systems. Grover's algorithm speeds up database searches and optimization problems. Quantum simulation models quantum systems, molecules, materials, chemical reactions naturally. Since quantum computers themselves are quantum systems, this could revolutionize drug discovery, material science, and our understanding of complex quantum phenomena. The challenge: decoherence. Qubits are incredibly fragile. Heat, electromagnetic noise, even stray particles can destroy the quantum state, a problem called decoherence. To maintain quantum coherence, qubits must be isolated in ultra-cold environments, near absolute zero, and shielded from interference. This makes building practical quantum computers extremely challenging. Different platforms use different physical systems, trapped ions, individual atoms held by electric fields, superconducting circuits, tiny loops of metal with zero resistance, photons, particles of light. Each approach has advantages and limitations. The field is still experimental, like the early days of classical computing. Current STIS quantum computers with dozens of qubits already exist. Companies and research labs worldwide are racing to build larger, more stable systems. Some quantum computers are even accessible online for experiments. We're still in the early stages, bicycle, not rocket ship, but the road is being paved toward a quantum future. Why it matters quantum computing represents more than faster calculations. It's a new paradigm, thinking in probabilities instead of certainties, exploiting superposition and entanglement as computational resources. It reminds us that information itself has a quantum foundation, and that the universe's strange rules at the small scales might unlock solutions to humanity's biggest challenges. The measurement problem quantum mechanics works brilliantly. Its predictions are stunningly accurate, yet after a century, physicists still debate what it actually means. We know how to calculate quantum outcomes, but what is the wave function? Does it represent something real or just our knowledge? Does the universe split with each measurement? Is there a hidden reality beneath quantum randomness? Different interpretations offer different answers. Copenhagen, shut up and calculate. The Copenhagen interpretation, developed by Niels Bohr and colleagues, is the traditional view. It says, the wave function is a tool for predicting measurement outcomes. Nothing more. Quantum systems don't have definite properties until measurement causes the wave function to collapse into a single outcome. Don't ask what's really happening. The theory works. Be satisfied with that. Copenhagen is pragmatic and clean, but philosophically unsatisfying. It refuses to explain what the wave function represents or why measurement is special. Many worlds. Everything happens. Hugh Everett III's many worlds interpretation, proposed in 1957, eliminates wave function collapse entirely. Instead, every possible outcome of quantum measurement occurs in different branches of reality. When you measure a particle's spin, the universe splits. In one branch, you see spin up. In another, a copy of you sees spin down. All possibilities are realized. We just experience one branch. The wave function never collapses. It continuously evolves according to the Schrödinger equation, and reality endlessly branches into a vast multiverse of parallel universes. What we perceive as collapse is actually decoherence, our branch of the universe becoming entangled with one particular outcome, while other branches realize other outcomes. In this view, Schrödinger's cat isn't a paradox at all. When you open the box, the universe splits. In one branch, the cat is alive. In another, it's dead. Both outcomes are equally real, just in different branches. You don't see both because your consciousness exists in only one branch. This interpretation has several appealing features. It's mathematically elegant, using only the standard quantum formalism without adding collapse as a separate process. It's deterministic. The universal wave function evolves smoothly and predictably. It treats all physical systems, including observers, the same way. There's no special boundary between quantum and classical realms. But many worlds comes with a hefty metaphysical price tag. It implies countless versions of you exist, making divergent choices at every quantum moment. Every time a quantum event occurs anywhere in the universe, which is constantly, reality branches. The number of parallel universes grows exponentially with every passing moment. Critics ask, if all outcomes happen, why do we experience particular outcomes with specific probabilities? The Born rule. The formula giving quantum probabilities must be derived from the branching structure itself, which has proven technically challenging. Also, can we really believe in countless unobservable parallel universes just to avoid wave function collapse? Supporters counter that many worlds is the simplest interpretation mathematically, that it takes the quantum formalism at face value without adding extra mechanisms, and that the existence of other branches is a prediction of the theory, not an additional assumption. Pilot wave. Hidden determinism. David Bohm's pilot wave theory, Bohmian mechanics, developed in the 1950s building on earlier work by Louis de Broglie, restores classical realism to quantum mechanics. Particles always have definite positions and velocities. They're never in superposition. They're guided by a pilot wave die, the wave function itself. The wave doesn't represent probability or potential. It's a real physical field directing particle motion through space. Like a surfer riding ocean swells, particles follow paths determined by the guiding wave. Quantum weirdness, interference, tunneling, arises naturally from this guidance mechanism. In the double slit experiment, both slits remain open and the pilot wave passes through both, creating an interference pattern in the wave field itself. The particle goes through only one slit, but is guided by this interference pattern in the pilot wave, producing the observed distribution even when particles are sent one at a time. Pilot wave theory is deterministic. There's no fundamental randomness. If you knew all initial conditions perfectly, positions and velocities of all particles, plus the wave function, you could predict everything. The apparent randomness we observe comes from our ignorance precise initial conditions, not from indeterminacy in nature itself. This has philosophical appeal. The world is real and definite at all times, not fuzzy and potential. Particles actually are somewhere, doing something, even when we're not looking. There's no measurement problem because measurement is just another physical interaction. No special collapse mechanism needed. However, pilot wave theory requires accepting non-locality. The guiding wave exists in configuration space, a higher dimensional mathematical space, and its influence on particles can be instantaneous across space. When you measure one entangled particle, it affects the pilot wave immediately, which instantly changes the guidance of the other particle, no matter how distant. This quantum non-locality is built into the theory, not something to be explained away. Critics note that the pilot wave itself is never directly observable. We only see the particles. Why believe in this invisible guiding field? Supporters respond that it provides a complete, deterministic, and intuitively satisfying account of quantum phenomena, while making identical predictions to standard quantum mechanics. Objective collapse. Reality decides. Some theories propose wave functions spontaneously collapse without observation, a real physical process happening randomly over time, especially as systems grow larger. The GRW, Gherardi-Rimini-Weber theory adds random collapse events to quantum mechanics. For small systems, collapse is rare. For large objects, frequent enough to eliminate superposition quickly. This explains why we don't see macroscopic superpositions, no quantum cats. Without requiring conscious observers, reality itself makes the choice. Cubism, it's about belief. Quantum Bayesianism, cubism, treats the wave function as subjective, representing an agent's personal beliefs about measurement outcomes, not objective reality. Measurement doesn't collapse an external wave function. It updates your knowledge. Quantum mechanics becomes a tool for rational decision-making under uncertainty, rather than a description of objective reality. Cubism is intellectually sophisticated, but sidesteps the question of what's actually out there. The verdict? No interpretation is proven. All fit the experiments. The question, what does quantum mechanics mean, remains open after a century. Perhaps you don't need to choose. Like quantum systems themselves, your understanding can exist in superposition, entertaining multiple possibilities without committing to a single answer. The math is clear. The predictions are precise. The meaning? That's still wonderfully mysterious. From atoms to stars, quantum mechanics isn't confined to microscopes and particle accelerators. It shapes the cosmos itself, atomic structure. Electrons occupy quantized energy levels, giving atoms stability and structure. Without quantum rules, atoms would collapse, chemistry wouldn't exist, and neither would we. Chemical bonds, every molecular bond, covalent, ionic, hydrogen, heiresses from quantum mechanics. Electron orbitals determine how atoms connect, what angles bonds form, what colors materials reflect. All of biochemistry, the entire machinery of life, runs on quantum chemistry. Stellar alchemy stars shine through nuclear fusion, powered by quantum tunneling. Without it, protons couldn't overcome electromagnetic repulsion to fuse, and stars would be cold, dead spheres. When stars die, quantum mechanics still governs their fate. White dwarfs resist collapse through electron degeneracy pressure. The Pauli exclusion principle preventing electrons from occupying the same quantum state. Neutron stars rely on similar quantum pressure from neutrons. Black holes push quantum theory to its limits, where gravity becomes so extreme that space and time themselves break down. The early universe, the universe's large-scale structure, galaxies, clusters, cosmic webs, may ultimately trace back to quantum fluctuations in the early universe. Tiny quantum uncertainties, amplified by cosmic inflation, became the density variations that seeded galaxy formation. In this view, quantum randomness sculpted the cosmos. Everything you see, stars, planets, life, emerged from ancient quantum jitters, amplified to cosmic scale. The classical world emerges. Why don't we see quantum effects in daily life? Because of statistics and decoherence. When trillions of quantum particles act collectively, their individual uncertainties average out. The result, classical, predictable behavior emerges from quantum foundations. A table is stable because its atoms are stable. Its atoms are stable because electrons obey quantum rules. Solidity is built on uncertainty. Quantum mechanics underlies everything, even when invisible. Myth 1. Your thoughts shape reality claim. Quantum physics proves consciousness creates reality. By focusing your intention, you can change the physical world, reality. Observation in quantum mechanics means measurement, distinctions between a quantum system and measuring device. It doesn't require human consciousness. A Geiger counter, photon detector, or stray particle can collapse wave functions. Your thoughts, wonderful though they are, don't control electron trajectories or bend reality to your will. Observation is physical interaction, not conscious awareness. Myth 2. Entanglement enables faster than light communication claim. Entangled particles let you send instant messages across any distance. Reality. While entanglement creates instantaneous correlations, it can't transmit information faster than light. When you measure your entangled particle, the result is random. The person far away also gets a random result. Only when you compare results later, via classical communication, obeying light speed, do you notice the correlation. No signal travels faster than light. No data is transmitted. Entanglement is strange but respects Einstein's speed limit. Myth 3. Schrödinger's cat actually dead and alive claim. The cat in the box genuinely exists in a dual state until observed. Reality. Schrödinger's cat is a thought experiment highlighting the absurdity of applying quantum rules to large objects, not a literal prediction. Decoherence prevents macroscopic objects like cats from maintaining superposition. Constant environmental interaction, air molecules, photons, vibrations, collapses quantum states almost instantly. No actual cat ever exists in a ghostly alive and dead limbo. The thought experiment is philosophical provocation, not physical prediction. Myth 4. Quantum physics is totally random and chaotic claim. Quantum mechanics means anything can happen anytime, pure chaos. Reality. Quantum mechanics is deeply structured, governed by precise mathematical laws that predict probabilities with extraordinary accuracy. Yes, individual outcomes are probabilistic, but the probabilities themselves follow strict rules. It's statistical. Like weather, we can't predict every raindrop, but we can model the system accurately. Randomness exists, but it's cradled in order. Myth 5. Quantum physics means anything is possible claim. If quantum effects allow particles to tunnel through barriers, then anything goes. Telepathy, magic, breaking physical laws by willpower. Reality. Quantum physics allows strange phenomena but within strict boundaries. Conservation laws still hold. Particles can't exceed light speed. Energy can't be created from nothing. Quantum mechanics expands what nature can do but doesn't throw out logic or evidence. It's one of the most rigorously tested theories in science, not a blank check for wishful thinking. The real magic. The truth is more wonderful than the myths. Quantum mechanics doesn't require us to reshape reality with our minds. It reveals that reality itself is strange, interconnected, and participatory. Observation shapes outcomes, not because consciousness is magical, but because measurement is interaction. We're woven into the universe, not separate from it. That's the real quantum insight. Reality emerges from relationships, not isolated objects, and that's profound enough without embellishment. What we've learned, we've journeyed from particles behaving like waves through the double slit experiment to superposition, where particles exist in multiple states simultaneously. We've explored the uncertainty principle, the fundamental limits on knowledge built into nature itself, and entanglement, the mysterious connections spanning space, linking particles that have interacted into a shared quantum state. We've seen how quantum field theory reveals particles as ripples in universal fields permeating all of space, how tunneling allows particles to pass through classically impenetrable barriers, and how life itself might exploit quantum coherence and entanglement. We've glimpsed quantum computing's revolutionary promise to solve problems beyond classical computation's reach and grappled with competing interpretations of what quantum mechanics fundamentally means. We've discovered that the sun shines because of quantum tunneling, that birds may navigate using quantum compasses, that photosynthesis achieves remarkable efficiency through quantum coherence, and that every technology we depend on, from smartphones to medical imaging, relies on quantum principles. Throughout this journey, one theme emerges repeatedly. The universe is stranger, more subtle, and more interconnected than common sense suggests. The solid, predictable world of everyday experience emerges from a quantum foundation that is probabilistic, holistic, and deeply counterintuitive. The quantum world is your world. You don't just live in a quantum universe. You are quantum. Every atom in your body obeys these bizarre rules. Every chemical reaction enabling your metabolism, every neural firing creating your thoughts, every heartbeat pumping your blood flows from quantum foundations. The electrons in your cells exist in quantized energy levels. The bonds holding your molecules together arise from quantum mechanical interactions. The photons hitting your retinas obey wave-particle duality. The uncertainty principle prevents your atoms from collapse. You are, quite literally, a walking, talking quantum system. The solidity you feel isn't separate from quantum mechanics. It merges from it. The colors you see exist because of quantum transitions. The life you experience depends on quantum tunneling in cellular respiration, quantum effects in enzyme catalysis, and possibly quantum processes in DNA replication and mutation. You're not separate from the quantum world, observing it from outside. You're part of it, woven into its fabric, a temporary but exquisitely complex pattern in the universal quantum field. The gift of mystery quantum mechanics teaches profound humility. After more than a century of intensive study by some of humanity's greatest minds, we still debate what it fundamentally means. We calculate with stunning precision. Quantum electrodynamics makes predictions accurate to 10 decimal places, the most precisely tested theory in science. Yet we argue about interpretation, about what the mathematics is telling us about reality. This isn't failure, it's an invitation. The universe, at its deepest level, resists being fully known in the way we once imagined. The deterministic, clockwork universe of Newton, where perfect knowledge of initial conditions could predict all future states, has given way to something stranger and richer. Mystery isn't a bug in the system, it's fundamental. Uncertainty isn't ignorance to be overcome with better instruments. It's woven into the fabric of nature. Superposition isn't confusion about what state something is in. It's the genuine existence of multiple states. Entanglement isn't explainable by hidden signals. It's real non-local correlation. And in that irreducible mystery lies profound wonder. Reality isn't fixed and determined, grinding mechanistically forward. It's fluid, participatory, responsive. Observation genuinely matters, not because consciousness is magical, but because interaction and measurement are physical processes that affect outcomes. Context shapes what we find. The act of asking questions influences the answers nature gives. This participatory universe, where we're not separate observers but entangled participants, is far more interesting than a clockwork cosmos would be. We don't just discover what was always there, predetermined and fixed. We engage in an ongoing dialogue with nature, where the questions we ask help determine the reality we uncover. The practical and the profound quantum physics isn't just philosophical speculation or mathematical abstraction. It's intensely practical, powering the technological civilization we inhabit. Consider what depends on our quantum understanding. Electronics. Every transistor in every computer, smartphone, and electronic device operates based on quantum mechanics. Semiconductors work because of quantum properties of materials, band gaps, electron behavior in crystals, tunneling through barriers. Lasers, from barcode scanners to fiber optic communication to surgical tools, lasers depend on stimulated emission, a purely quantum phenomenon where photons trigger atoms to release additional photons in phase. Medical imaging. MRI machines exploit quantum spin properties of atomic nuclei. PET scans use antimatter, positrons annihilating with electrons, a quantum process. Radiation therapy uses quantum tunneling and radioactive decay, GPS and atomic clocks. Ultra-precise timekeeping relies on quantum transitions in atoms. Without accounting for quantum effects and relativistic corrections, GPS would drift by kilometers per day. Solar cells and LEDs, photovoltaic conversion and light-emitting diodes both work through quantum mechanical processes. Electrons jumping between energy bands, photons being absorbed or emitted. Chemistry and materials. All of materials science, pharmaceutical development, and chemical engineering rests on quantum mechanical understanding of atomic and molecular behavior. Every new material, every drug molecule, every catalyst is designed using quantum principles. Future quantum technologies promise even more. Quantum computers solving previously intractable problems, quantum cryptography providing unbreakable, secure communication, quantum sensors detecting gravitational waves, measuring magnetic fields with unprecedented precision, quantum metrology. enabling measurements at fundamental limits. But beyond practical applications, quantum mechanics offers something deeper, a new way of seeing reality. It asks us to embrace uncertainty rather than fight it, to appreciate interconnection over isolation, to accept that the world contains more possibilities than we can exhaust or even imagine. It challenges us to think in probabilities rather than certainties, in relationships rather than independent objects, in complementary perspectives rather than single absolute viewpoints. These aren't just physics lessons. They're philosophical insights applicable far beyond the laboratory. Closing thoughts. So here we are, at the end of our quantum journey through the most astonishing scientific framework ever developed. The universe, as quantum mechanics reveals it, is made not of things but of relationships and interactions. Not of certainties, but of probabilities weighted by complex amplitudes. Not of isolated, independent objects, but of entangled, interconnected systems. Particles exist in superposition of multiple states until observation collapses possibilities into actuality. The act of measurement doesn't just reveal reality, it participates in creating it. Distance doesn't always separate. Entangled particles remain correlated across vast expanses of space. Barriers aren't absolute. Particles can tunnel through them. The vacuum isn't empty. It seethes with virtual fluctuations. Time and energy, position and momentum are linked by uncertainty relations that limit knowledge itself. And you, made of stardust forged in stellar cores, governed by quantum rules inherited from the universe's birth, organized into complex structures that can contemplate their own existence, are part of this magnificent cosmic dance. You're not separate from the quantum world, observing from outside. You're in it, of it, woven through its very fabric. Every breath you take involves quantum chemistry. Every color you perceive results from quantum transitions. Every thought arises from quantum processes in neurons. The stability of matter, the possibility of chemistry, the power of stars, all depend on quantum principles that seemed utterly bizarre when first discovered, but are now recognized as fundamental to existence itself. As you reflect on what you've learned, or as you drift towards sleep, carry this with you. Beneath the ordinary surface of reality lies extraordinary depth. The world is far stranger and more beautiful than common sense suggests. It's built on probabilities and possibilities, on wave functions and superpositions, on entanglement and uncertainty. And that strangeness isn't something to fear or reject. It's an invitation to wonder deeply, to question boldly, to explore openly, to embrace the magnificent quantum weird, utterly astonishing, endlessly fascinating universe we're privileged to inhabit. The quantum world seemed impossible when first discovered. Particles behaving like waves, existing in multiple places simultaneously, instantaneous correlations across cosmic distances. It all seemed too strange to be true, but nature doesn't care what seems reasonable to creatures who evolved to throw rocks and avoid predators. Nature simply is what it is. And what it is, as quantum mechanics reveals, is more subtle, more interconnected, more possibility-rich than anyone imagined. Perhaps the deepest lesson of quantum mechanics isn't about particles or waves, uncertainty or entanglement. Perhaps it's this: the universe is knowable but not completely knowable, ordered but not deterministic, connected but not mechanistic. It leaves room for mystery, for probability, for genuine novelty. It's a cosmos that invites exploration while remaining fundamentally inexhaustible. In a universe governed by quantum mechanics, you are both observer and participant, both wave and particle, both determined by past events and open to future possibilities. You are, in the deepest sense, quantum, a temporary but magnificent pattern in the eternal dance of possibility and actuality. Thank you for joining this journey through quantum physics. May you always maintain wonder at the strange and beautiful cosmos you inhabit. May you embrace uncertainty as fundamental rather than problematic. May you see interconnection where others see separation. And may you never lose the sense of astonishment at the universe. This quantum, probabilistic, entangled, superposed, tunneling, wave-particled universe exists at all, and that you are part of it. Sweet dreams. Or, in quantum terms, may your consciousness explore all possible dream states in superposition until morning's observation collapses the wave function and you wake to experience just one, hopefully well-rested, outcome.